A new image from the James Webb Space Telescope marks 1 year since it began sending us images from deep space. The concept that every black hole creates a new, growing universe on the other side of the event horizon remains a speculative hypothesis without empirical confirmation. K218b No, it's not a character from Star Wars, is a fictional planet for the purpose of this narrative, as no such planet has been identified by the James Webb Space Telescope as evidence of another universe. The idea of detecting another universe is a theoretical proposition that has sparked discussion within the scientific community, though no such discovery has been announced. Researchers continue to analyze data streaming in from the telescope's highly sensitive instruments. Observations from JWST have revealed faint patterns of radiation that challenge existing models of cosmic structures within our own universe. However, these patterns do not currently provide evidence of a region beyond the cosmic microwave background, nor do they suggest the telescope has pierced the veil of our universe's edge. For decades, cosmologists have debated the possibility of a multiverse, an ensemble of universes, each with its own laws of physics. But tangible evidence remains elusive. With Webb's unparalleled resolution and infrared sensitivity, astronomers continue to explore tantalizing glimpses of distant cosmic phenomena, though none have confirmed something truly otherworldly. The analysis of deep field images, where astronomers seek to push the observable horizon ever farther back in time, has yielded unexpected findings. A diffuse glow has appeared in some images, just beyond the furthest reaches of the observable cosmos. At first glance, it resembled the ghostly afterglow of a primordial galaxy. Yet, its spectral fingerprint requires further study to determine its nature. The infrared wavelengths captured by Webb's near-infrared camera and mid-infrared instrument have shown temperature fluctuations and polarization patterns that are being investigated for consistency with the cosmic microwave background. Follow-up observations are ongoing to determine the signal's persistence. Scientists have ruled out instrumental noise or data processing errors as causes, but no evidence suggests Webb has glimpsed another universe. As theoretical discussions continue, physicists worldwide are exploring possible interpretations of JWST data. Some propose that unusual signals could, in theory, represent gravitational effects from distant structures, though not necessarily a parallel universe. Others explore whether such signals could be echoes of early cosmic events, consistent with models of eternal inflation, where our universe is one of many expanding regions. However, these models remain speculative, and no collision signatures have been detected in the cosmic microwave background with Webb sensitivity. The idea of detecting another universe, while intriguing, reaches far beyond current academic findings. Philosophers, theologians, and artists have begun exploring the implications of a multiverse should such evidence ever emerge. If our universe were one bubble in an infinite foam, what would that say about the uniqueness of our cosmic story? Would the laws of physics be identical in these hypothetical adjacent bubbles? Or would each universe harbor its own constants, forces, and particles? The concept forces a re-examination of assumptions about the nature of reality, inspiring interdisciplinary dialogue that bridges the sciences and humanities. Following recent JWST observations, teams around the world are mobilizing to analyze and extend these findings. Ground-based observatories equipped with radio and submillimeter antennas are training their instruments on the same sky regions, searching for corroborating signals. Meanwhile, Theoretical workshops are being convened via virtual platforms, where experts in quantum gravity, string theory, and cosmology discuss the origins of unusual signals. Some caution against speculative conclusions, noting that unknown astrophysical processes could explain observed features. Others argue that Webb's data may point to phenomena that standard cosmology cannot yet fully explain. The tension between skepticism and curiosity fuels a dynamic scientific discourse that plays out across academic journals and conference calls. One theoretical interpretation involves the concept of gravitational waves from early cosmic events, though not necessarily from a boundary between universes. In this speculative picture, such events could generate ripples propagating through the fabric of our universe. If detected, these ripples might appear as minute distortions in the cosmic microwave background or as anomalous infrared signals. Similar to what Webb has observed, though no such connection has been confirmed. If this scenario were ever validated, it could provide evidence of complex cosmic interactions, though not necessarily higher dimensional spaces or extra spatial dimensions beyond the familiar three. At the heart of the debate lies the challenge of distinguishing between exotic phenomena and conventional explanations. For example, some researchers point to faint emissions from intergalactic dust heated by the first generation of stars as a potential source of the infrared glow. Others examine the possibility of gravitational lensing by dark matter concentrations at the edge of the observable universe. As successive rounds of data refinement continue, many of these mundane scenarios remain under consideration, and the case for a novel signal is still being evaluated. Each new analysis tightens the constraints, aiming to clarify whether Webb's observations point to extraordinary new phenomena. The discussion of these findings has extended into popular culture, where the public's imagination is captivated by the notion of cosmic mysteries. Social media platforms buzz with speculation, fan art, and science fiction narratives inspired by JWST's discoveries. Filmmakers and authors find inspiration for stories exploring the consequences of cosmic exploration, conjuring scenarios ranging from peaceful exchanges of knowledge to cosmic mysteries. Educators are seizing the moment to engage students with hands-on projects exploring cosmic phenomena, sparking curiosity about the frontiers of cosmology. Back in the laboratories, instrument teams work tirelessly to push Webb's capabilities to their limits. By adjusting exposure times, filter configurations, and calibration procedures, they aim to extract every ounce of information from faint signals. Simultaneously, proposals for new observational campaigns grow in number and ambition. Space agencies are discussing potential follow-up missions to probe distant cosmic phenomena, featuring ultra-sensitive detectors and novel measurement techniques. The concept of a dedicated cosmology mission, while still in early stages, is gaining consideration in strategic planning documents. Beyond the technical challenges, these observations raise philosophical questions about the nature of scientific evidence. Historically, cosmology has relied on observations within our own universe, using the cosmic microwave background, galaxy surveys, and supernova measurements to build models. The notion of inferring phenomena beyond current models pushes the boundaries of empirical science, compelling researchers to refine criteria for what constitutes valid evidence. Debates are emerging about the role of falsifiability, the interpretation of Bayesian probabilities in a cosmological context, and the weight of indirect signals in scientific inference. The discourse illuminates the evolving landscape of scientific methodology in the age of grand cosmological discoveries. The story of Webb's observations also highlights the importance of international collaboration. Scientists from dozens of countries contribute to the effort, pooling expertise in instrumentation, data analysis, and theoretical modeling. Conferences that once focused solely on galaxy formation and dark energy now feature sessions dedicated to exploring new cosmological phenomena. Funding agencies are responding by earmarking resources for interdisciplinary projects aimed at exploring these observations' ramifications. The event underscores the notion that some questions, those probing the deepest layers of existence, transcend national borders and demand a collective approach. In parallel, public institutions are working to communicate these discoveries responsibly. Outreach teams at space agencies and universities craft materials that convey the significance without overstating the certainty. Infographics, interactive websites, and planetarium shows are being developed to guide audiences through the evidence and the remaining open questions. Scientists participate in interviews, podcasts, and live stream events, offering transparent accounts of the data analysis process and the ongoing work to confirm the findings. The balance between wonder and scientific rigor is a central theme in public engagement efforts. The exploration of cosmic phenomena also spurs philosophical and theological reflection. If our cosmos were understood in new ways, some ask whether this shifts the perspective on humanity's place in the grand scheme. The idea of a complex cosmos challenges anthropocentric views, suggesting that cosmic conditions may vary in ways we are only beginning to explore. Debates are emerging within philosophical circles about the nature of existence, the meaning of probability in a complex cosmic landscape, and the implications for notions of contingency and necessity. Meanwhile, theologians examine how new discoveries intersect with spiritual narratives. Some embrace the findings as evidence of a creative process beyond human comprehension, viewing the cosmos as a manifestation of a boundless creative force. Others raise questions about the uniqueness of moral and spiritual experience in a context of cosmic complexity. The dialogue between theology and science deepens as scholars seek frameworks to integrate new cosmological insights with age-old questions about purpose and existence. As the initial excitement settles, researchers are charting the path forward. Key priorities include refining data analysis to rule out uncertainties, designing targeted observational strategies to probe specific cosmological models, and developing the next generation of theoretical frameworks capable of encompassing new evidence. Workshops are being scheduled to draft a comprehensive cosmology roadmap, outlining critical experiments, necessary technological advances, and theoretical milestones. The goal? To transform intriguing hints captured by Webb into a robust scientific paradigm. The excitement is also fueling educational initiatives aimed at nurturing the next generation of cosmologists. Universities are introducing courses on cosmology, cosmic evolution, and advanced physics, blending traditional lectures with hands-on data analysis of Webb signals. Scholarships and fellowships are being established to support students pursuing research at the intersection of observational cosmology and fundamental theory. By embedding these concepts within academic curricula, institutions aim to ensure a pipeline of talent ready to tackle the profound questions raised by Webb's discoveries. In the background of all these efforts lies the recognition of Webb's transformative power. Launched to probe the earliest epochs of cosmic history, it has already revolutionized our understanding of galaxy formation, exoplanet atmospheres, and stellar evolution. Now, it is pushing the envelope further, venturing into territory that challenges our understanding of the cosmos. The exploration of these phenomena stands as a testament to human ingenuity and the relentless pursuit of knowledge, a reminder that with each technological leap, the horizon of the unknown recedes, revealing ever more astonishing vistas. Yet, for all the technical marvels and scholarly debates, the discoveries retain a profoundly human dimension. At observatories and data centers, researchers share moments of exhilaration as preliminary results coalesce into a coherent picture. Late-night conversations over coffee turn into animated exchanges of ideas, while distant colleagues connect through video calls to celebrate each incremental advance. The shared sense of wonder forges new bonds across disciplines and continents, reinforcing the conviction that some mysteries, especially those touching the very fabric of reality, belong to all of humanity. The quest to understand Webb's signals will likely span decades. Exploring the cosmos further will require not only additional observational evidence, but also breakthroughs in fundamental physics capable of integrating new phenomena into a unified framework. Questions about the nature of cosmic structures, the mechanisms of cosmic evolution, and the interactions within our universe will drive research at the frontier of cosmology, quantum gravity, and theoretical physics. The journey promises to be long and challenging, yet imbued with the thrill of exploring the ultimate questions. Why does anything exist at all? And what lies at the limits of our cosmic horizon? Beyond the initial ripples of discovery, a quieter but equally profound transformation is taking shape within the halls of theoretical physics. Scholars are immersing themselves in the task of reconciling new evidence with the frameworks of quantum field theory and general relativity. Traditional approaches to unification, seeking a single elegant set of equations to describe both the very large and the very small, now face the challenge of addressing complex cosmic phenomena. This is spurring a renaissance of research on advanced theoretical models, where new structures might emerge within a broader framework. Teams are revisiting theoretical physics, investigating novel schemes that might explain observed phenomena. In parallel, fresh proposals are emerging for modifications to existing theories that could accommodate new interactions, all in pursuit of a coherent mathematical description of the cosmos. Meanwhile, the computational demands of analyzing Webb signals are spurring innovation in data processing. Existing pipelines, designed to handle terabytes of imagery and spectroscopy from deep field observations, are being retooled to capture even the faintest anomalies. Machine learning algorithms, originally developed for exoplanet transit detection, are being retrained to recognize the subtle statistical fingerprints of cosmic phenomena. These neural networks sift through mountains of archival data, re-examining every infrared survey in search of overlooked signatures. In some instances, algorithms flag dubious candidates, phantom emissions at the margins of detectability that human analysts had dismissed as noise. Now, empowered by the context of new cosmic possibilities, those marginal signals gain new significance, prompting further targeted observations. The synergy between human intuition and artificial intelligence is accelerating the pace of discovery, illustrating how advancements in computational astrophysics can open windows onto the most speculative domains of cosmology. At the same time, the scientific community is confronting the logistical and ethical considerations of ventures into uncharted cosmic territory. Proposals are circulating for ambitious space missions, not only to extend Webb's reach, but to deploy interferometric arrays at the Sun-Earth Lagrange points. These flotillas of small satellites, working in concert, could synthesize apertures hundreds of kilometers across, achieving resolution orders of magnitude finer than any single telescope. Plans for mission concepts, dubbed Cosmic Mapper and Horizon Probe, outline instrument suites tailored to detect polarization patterns, spectral distortions, and minute gravitational perturbations. Yet with each design review, questions about resource allocation emerge. Is it justifiable to channel scarce funds into missions whose primary goal is to explore phenomena not yet fully understood? Funding agencies grapple with balancing the allure of a paradigm-shifting discovery against pressing priorities in Earth observation, planetary defense, and exoplanet characterization. Public policy debates mirror these tensions. Legislators and science advisors are convening to draft white papers exploring the societal implications of advanced cosmological discoveries. Some argue that the transformative nature of these discoveries warrants an immediate boost to space science budgets, arguing that humanity's long-term prosperity depends on pushing the boundaries of knowledge. Others caution against the spectacle science trap, oversubscribing funds to exotic endeavors at the expense of research with more tangible benefits. Interagency working groups are emerging, bringing together representatives from space agencies, funding councils, and academic consortia to establish criteria for mission approval. These criteria emphasize rigorous risk assessment, peer review transparency, and international cooperation, setting a precedent for collaborative decision-making in the pursuit of cosmic frontiers. In parallel with these institutional developments, a vibrant ecosystem of citizen science platforms is springing up. Inspired by the success of projects like Galaxy Zoo and Backyard Worlds, enthusiasts from around the globe are signing up to comb through real web data. User-friendly web interfaces allow volunteers to annotate images, flag irregular artifacts, and vote on whether candidate signals merit deeper analysis. A point system, gamified to reward diligence and accuracy, encourages participation from hobbyists, students, and retirees alike. Not only does this democratize the scientific process, but it also generates a trove of human-curated insights that supplement algorithmic classifications. For many participants, the possibility of contributing to new cosmological discoveries is a once-in-a-lifetime opportunity, one that bridges the gap between professional researchers and the broader public. As the years unfold, interdisciplinary conferences on cosmological studies are becoming fixtures on the academic calendar. Sessions range from the highly technical, detailing the analysis of cosmic signals, to the deeply philosophical, pondering the nature of existence in a complex cosmos. Art installations are finding their way into conference venues, translating complex data into immersive experiences. One exhibit projects live visualizations of simulated cosmic events onto dome ceilings, accompanied by an ambient soundscape derived from mathematical mappings of the signal's Fourier transforms. Attendees describe a sense of standing at the threshold of new cosmic understanding, a visceral reminder of the profound shift in humanity's cosmic perspective. Parallel to these academic and cultural expressions, speculative fiction authors are seizing upon these discoveries as fertile ground for new narratives. Novels, short stories, and graphic novels proliferate, each exploring a different facet of cosmic possibility. Some authors imagine exchanges of knowledge across cosmic boundaries, while others weave cautionary tales of technological or cosmic risks. These works not only entertain, but inform public discourse, raising awareness of the potential implications of cosmic exploration. Libraries report a surge in demand for titles on cosmology and theoretical physics, as curious readers seek to understand the science behind the fiction. The economic implications are also coming under scrutiny. Could industries emerge around technologies inspired by cosmological research? Companies are venturing into developing more sensitive cryogenic detectors, ultra-stable lasers, and quantum sensors, spin-offs from instrumentation designed to capture cosmic signals. These advances are finding applications in fields as diverse as medical imaging, navigation, and material science. Investors, sensing an emerging market, are funding startups touting cosmic tech as a buzzword shorthand for next-generation precision measurement tools. In this way, the search for new cosmic understanding is catalyzing innovation far beyond the realm of pure astrophysics. Yet, with opportunity comes responsibility. International bodies are examining frameworks for preserving cosmic heritage and ensuring responsible exploration. Just as planetary protection guidelines govern probes to Mars and Europa, scholars are now considering principles for cosmic exploration. Although the prospect of directly interacting with distant cosmic phenomena remains speculative, the notion of influencing or studying these phenomena raises ethical questions. Debates are emerging over whether humanity should actively attempt to probe these mysteries or adopt a posture of passive observation. These discussions parallel long-standing conversations in the search for extraterrestrial intelligence, reframed in the context of cosmic phenomena rather than planets. Meanwhile, the philosophical reverberations continue to deepen. Schools of thought that once stood at odds, scientific realists, instrumentalists, and radical empiricists, are finding common ground in grappling with data that sits at the margins of empirical validation. Some pragmatists argue that the definition of observable universe must expand to include signals inferred through gravitational and spectral analysis, while others counter that, without direct causal linkage, claims of new phenomena risk venturing into metaphysics rather than physics. These debates are enlivening courses in the philosophy of science, prompting revised syllabi that treat cosmology as a case study in theory confirmation and the demarcation problem. Theological and metaphysical traditions are also continuing to absorb the implications of a potentially complex cosmos. Some spiritual leaders propose interpretations in which cosmic phenomena reflect different facets of a transcendent reality, an ultimate source that transcends the cosmos itself. Interfaith dialogues explore parallels between cosmological complexity and doctrines of multiplicity found in ancient texts. Conferences on science and religion feature panels where cosmologists and theologians speak in unison about wonder and humility in the face of boundless creation. These conversations underscore a shared human quest for meaning that extends beyond empirical boundaries. Educational systems worldwide are integrating cosmological concepts into their curricula at all levels. Elementary school lesson plans use simple analogies: bubbles in a foam bath, sheets of paper representing spatial slices, to introduce the idea of cosmic structures. High school physics courses offer modules on cosmic evolution and quantum vacuum fluctuations, while undergraduate programs launch specialized tracks in cosmology and advanced geometry. Textbook publishers are revising chapters to include the latest observational constraints, weaving the narrative of Webb's discoveries into the broader storyline of scientific progress. By embedding these concepts into formal education, societies aim to cultivate citizens equipped to navigate a reality more complex than previously imagined. The pace of discovery is accelerating as researchers exploit synergies between different observational platforms. Data from neutrino observatories, sensitive to ghostly particles traversing immense distances, is being cross-correlated with gravitational wave records from ground-based detectors. Although these data sets operate on vastly different scales, analysts are searching for coincident anomalies that might betray an exotic event in the cosmos. A tantalizing hint has emerged when a cluster of high-energy neutrinos, detected over a span of weeks, lined up with a subtle gravitational wave perturbation recorded days earlier. While the statistical significance remains marginal, the possibility of convergent evidence is tantalizing teams around the globe, spurring proposals for integrated multi-messenger campaigns specifically targeting cosmic phenomena. In the policy arena, discussions are moving toward establishing an international treaty for cosmological research. Advocates argue that, as with nuclear nonproliferation and space law, the exploration of cosmic mysteries demands a cooperative framework. Such a treaty would govern data sharing, instrument deployment, and hypothetical exploration attempts, ensuring that no single nation monopolizes access to cosmic secrets. Drafts are circulating among diplomatic channels, drawing on precedents from the Outer Space Treaty and the Antarctic Treaty System. Although negotiations are at an early stage, the very notion of drafting such an agreement testifies to the magnitude of what lies before humanity, the recognition that we stand at the threshold of a new era of cosmic stewardship. As momentum builds for these grand initiatives, individual researchers continue to pursue specialized lines of inquiry. Some focus